Welcome to this explainer. When you picture the periodic table, you probably think of that familiar castle-like block you stared at in chemistry class, right? Well, today we are heading straight into the basement. I'm talking about those two disconnected rows, kind of banished to the very bottom of the chart. And far from being leftovers, these are the F-block elements. They are essentially the deeply buried secret ingredients powering our entire modern civilization.
So have you ever stopped to ask yourself what exactly makes your smartphone screen glow so vividly? Or what's actually spinning inside a massive wind turbine to generate all that electricity? What about the fuel for the immense power of a nuclear reactor? Well, the answer isn't just a generic technology. It's an invisible chemical force, and it's driven entirely by these specific, isolated elements hanging out at the bottom of the periodic table. Here's our roadmap for today. First, the periodic table's hidden rows. Then, lanthanides, rare earth workhorses. Third, actinides, radioactive powerhouses. Fourth, lanthanides versus actinides. And finally, powering the modern world. Let's dive right in with Section 1, the periodic table's hidden rows. Okay, so formally these elements are known as the inner transition elements. They actually belong right between the S block and the D block in periods 6 and 7. Honestly, the main reason they're usually shown separately is just to keep the periodic table compact, because otherwise the thing would be impossibly wide. But the absolutely crucial word to remember here is inner. In these elements, the new differentiating electrons, the ones that literally make an element unique, they aren't being added to the outside. Instead, they're diving deep into the F orbital, which is the third shell in. So these active F electrons are quite literally buried deep inside the atom, totally shielded from the outside world.
Looking at how they're structured, we basically have two distinct series. First, the lanthanides, which fill the 4f orbital and cover atomic numbers 57 to 71, and then the actinides, filling the 5f orbital from atomic numbers 89 to 103. Now, I know that general electronic configuration formula looks like an absolute alphabet soup, but really all it's telling us is that the f orbitals, which can hold up to 14 electrons, are being systematically filled deep within the atom, while that outer s shell stays relatively constant. Moving on to Section 2. Lanthanides, the rare earth workhorses. Fun fact, despite that rare earth nickname you've probably heard, these are actually true metals. They've got really high melting points, high densities, and they chemically favor a +3 oxidation state. But here is exactly where those buried F electrons start to show off a bit. Because those orbitals have complex shapes with unpaired electrons, these metals are actually paramagnetic, meaning they're weakly pulled toward magnets. And thanks to something called FF electronic transitions, their compounds are beautifully colored. For instance, the neodymium 3+ ion creates this absolutely brilliant, vivid purple. But as we move across this specific series, we run into one of the most fascinating things in all of chemistry. It's called the lanthanide contraction. This is a gradual, steady decrease in the size of the atoms and ions as you move from lanthanum to lutetium. Basically, as these atoms get heavier, they physically shrink. So why in the world do they shrink? Well, it all comes back to those deeply buried 4f electrons. As the atomic number goes up, the positive charge of the nucleus gets stronger. Normally, your inner electrons will shield the outer electrons from that nuclear pole. But here's the catch. 4f electrons are terrible at shielding. Because of that poor shielding, the nucleus just pulls the outer electrons in tighter and tighter, shrinking the atom. And this has massive, real-world consequences. It makes elements like zirconium and hafnium nearly identical in size and properties. It also makes lanthanides incredibly difficult to separate from one another, because their chemical behavior and ionic radii are virtually identical. Honestly, this gave early chemists absolute nightmares trying to pull them apart.
Which brings us to Section 3. Actinides, the radioactive powerhouses.
Now, unlike the lanthanides, where radioactivity is pretty much a rare exception, down here in the actinide series, it is the absolute rule. Every single actinide is radioactive. No exceptions. They are constantly decaying, spitting out alpha particles, beta particles, and gamma rays. A few of them do exist naturally, like uranium and thorium, but a whole lot of the others are completely synthetic. They're literally born only in laboratories or inside the extreme intense environments of nuclear reactors.
Another massive difference is their chemical flexibility. While the lanthanides stubbornly stick to that +3 charge we talked about, the actinides are wildly unpredictable. Uranium and plutonium, for example, can show states from +3 all the way up to +6. Neptunium even goes up to +7. This happens because their 5f, 6d, and 7s orbitals have very, very similar energy levels. So that means a whole lot more electrons can jump into the fray to participate in bonding, which allows them to form complex molecules way more readily than their cousins above them.
However, despite being so different, they do share a very familiar family trait. Just like the lanthanides, they suffer from the actinide contraction. As you move across the series, the ionic size gradually decreases. And the culprit? Exactly the same thing. The poor shielding effect. Only this time, it's the 5f electrons failing to protect those outer shells from the ever-growing nuclear charge. All right, section 4, lanthanides versus actinides. Let's just put these two head-to-head for a second to really lock in our understanding. Looking at the lanthanides, we see the 4f orbital at play. They're mostly non-radioactive, they really prefer that +3 oxidation state, and overall their reactivity is fairly moderate, meaning less covalent bonding. The actinides, on the other hand, driven by the 5f orbital, are a different beast entirely. They show highly variable oxidation states, their bonding is heavily covalent, they're highly reactive, and crucially, as we said, they are completely radioactive. Basically, those 5f electrons simply participate in bonding much more effectively than those deeply buried 4f electrons. And finally, section 5, powering the modern world. Now let's look at why you should care, because the applications for these elements are incredibly specific and totally essential. You literally cannot build a modern wind turbine or even those tiny, powerful motors in your headphones without neodymium magnets. That smoke detector keeping your house safe while you sleep, that actually relies on the radioactive decay of americium-241. Nuclear power, which releases huge amounts of energy through fission, is fueled by uranium-235 and plutonium-239. Even the pristine, scratch-free glass on your tablet or your smartphone was more than likely polished using cerium oxide. So it's no exaggeration to say these elements are the backbone of our most critical industries. Green energy relies on them heavily for electric vehicles and turbines. The electronics industry needs them for smartphones, computer hard drives, and fiber optics. Advanced defense applications absolutely depend on them for laser systems and missile guidance. Even medicine leans heavily on F-block elements for things like cancer treatments and MRI contrast agents. Without rare earth elements and actinides, manufacturing the technology of the 21st century would just grind to an absolute halt. But we have to address the elephant in the room. This incredible utility brings us to a massive, unavoidable challenge, the environmental cost. Remember the lanthanide contraction we talked about earlier? Because these elements shrink uniformly and act almost identically to one another, separating them requires incredibly intense, complex chemical processes. Mining and extracting these F-block elements often results in severe soil pollution, water pollution, and yes, even radioactive contamination. Proper disposal and recycling aren't just good ideas in this industry. They are absolute, bare minimum necessities to prevent widespread ecological damage. Yet, despite all these risks, the core truth of the matter remains exactly this. F-block elements have become indispensable in science and industry. Understanding their unique electronic structures, their magnetic properties, and their super complex chemistry doesn't just help us ace a chemistry test. It reveals exactly how deeply these hidden elements influence the very fabric of our modern civilization. Which leaves us with a pretty massive question to chew on. We know for a fact that these hidden inner transition elements are the engines of our progress, from the phones in our pockets to the massive power grids lighting our cities. But given the immense difficulty of extracting them and the serious pollution it generates, are the technological leaps they provide truly worth the radioactive and environmental footprint left behind? It's a complex chemistry problem that has evolved into one of the most vital questions of our time. Thanks so much for joining me on this explainer, and keep questioning the science around you.